and welcome, class. Today we're going to be finishing Chapter 6. So far we have learned the basics for how to draw Lewis structures using the generic kind of Lewis structure drawing approach. That was the entirety of our Part 1 lecture. And in our previous part we started introducing, I should say, more of the notable exceptions about either structures or the way that our chemical bonds work. So what we are going to be now wrapping up this lecture with is one last definition that's kind of necessary to really get into all of our exceptions to the octet rule. How do we know when we are allowed to actually break the octet rule in order to make a structure that would otherwise be unexpected but is actually more stable structure for this molecule to exist in? Alright, so first let's discuss what formal charge means using some less exceptional examples of Lewis structures, and then we're going to really start getting into these exceptions to the octet rule. Alright, so formal charge is used to determine the most plausible Lewis structure if there is more than one possible. This is also going to be different than resonance options. In a true resonance structure, like when we have more than one structures that we have to draw, like our previous examples were ozone and carbonate in Part 2's lecture, we needed multiple equal structures in order to kind of get an average for what the real molecule would be looking, how it would behave, what its characteristics would be. Formal charge is going to be necessary when it would appear as though we have the option to make a resonant structure, but it turns out that the options that we would end up drawing are not actually equal in energy. How do we know which of these options is actually going to be the correct option when we are not actually going to be in resonance? How we find formal charge: this is a measure of the number of electrons that are conventionally assigned to an atom in a molecular structure. It is going to be equal to the difference between the number of valence electrons a particular atom has. This is something really important about formal charge. It is assigned to atoms in the molecule. Formal charge is not assigned to the molecule on the whole. We are instead looking at the parts inside of the molecule and kind of picking out and determining whether or not the number of electrons that it is actually surrounded by in this molecular configuration is going to stabilize it by comparing that number to the number of valence electrons the particular atom normally has. So assuming a really nice stable formal charge, this is going to be equal to your valence electron count, again for a particular atom. We're going to subtract out the number of unshared electrons it has, so these are going to be the lone pair electrons, and we're going to count each electron individually, and we're going to add that to 1/2 of the shared electrons. These are the bonding pairs. So again, we're going to be looking at an atom and comparing how many electrons it's normally surrounded by, just off in its neutral form. And we're going to compare that to the number of electrons it's actually surrounded by in this particular molecular configuration. All right, we're going to be looking at an example of this by actually working through an example. When does paying attention really to formal charge actually do something for us versus when is it just busy work? Formal charge is useful to determining which structure, when multiple structures are available, which is going to be the most correct. The structure that has the most minimized formal charges, those that are closest to, if not all, equal to 0. We want the atom to be as comfortable in its environment as what it would be if it were off on its own. It needs to be surrounded by a number of electrons that is going to actually adhere to what its natural form is. if charges must be present, if you can't get a formal charge of 0, in this case, the most stable molecular structure is going to arise when the negative charge is on the most electronegative element, and the positive charge is going to be on the least electronegative element. Sometimes positives and negatives will both have to be present. Sometimes it'll just be a negative charge. Sometimes it'll just be a positive charge. It just depends on the molecule you're working with. The additional observation that we can make is that the sum of all of the formal charges across each of the atoms in the molecule will equal the overall charge of the molecule. So if you're working with something that is a neutral molecule, like what we have drawn below, and we're going to break this down, this means that the sum of each of the individual formal charges on the oxygen, the carbon, and the chlorines must also equal 0. This means that either the elements themselves could all have 0 formal charge, or if we have a single positive, we're also going to have a single negative or something like that. All right, so without further ado, right, let's see where formal charge actually comes into play and actually give some context for these kind of, hypothetical observations listed up above. So let's say I put you in charge of drawing the most stable molecular structure, the most stable Lewis structure for this molecule here, where we have 2 chlorines, a carbon, and an oxygen. Well, in following all of our previous Lewis structure drawing rules, carbon has the greatest bonding capacity, so we're going to put that in the middle. We've drawn our skeletal structure, as we can see illustrated here, and all of the electrons that are remaining in the pool have been placed around the oxygen and the chlorines. Now, there are no extra electrons left, but we can see that our carbon in the center is dissatisfied, right? There's only 2, 4, 6 electrons around it, which means we're going to have to pull a lone pair from one of the terminal atoms, either the oxygen or one of the chlorines. I mean, technically we could also pull from the other chlorine, but in this hypothetical example, I'm only going to be paying attention to the 2 different options here. And the reason why is because oxygen and chlorine are different, with different bonding strengths to the carbon, with different bond lengths to the carbon, these 2 options are not equivalent in energy. These 2 options will actually give us 2 unique structures, not 2 resonance structures. So if we follow the first option, where we draw out the lone pair moving from the oxygen in between that of the oxygen and carbon area, we're going to have a double bond up on top between the oxygen and the carbon, and our 2 single bonds will still remain on the 2 chlorines down below. Our second option, if we take the lone pair from chlorine and move that in instead, is going to look like our structure on the right. So the single bond is still present between the oxygen and the carbon in the middle. We now have a double bond to the chlorine down below on the left, and a single bond to the chlorine here on the right. Because these 2 bonding types, oxygen to carbon versus chlorine to carbon, are different, these are 2 different structures with different energies and different bond lengths. Therefore, this is a huge red flag. We should use formal charge to assess which of these 2 unique options is actually going to be more stable. So let's just start with our structure on the left, right? We'll just go from left to right. And I'm going to change color real quick. Blue. Perfect. Perfect. All right, so our structure on the left, we're going to calculate what the formal charge is for each of the atoms inside of this molecule. And we want minimized formal charges, right? We want formal charges as close to 0 as possible. So if, when we're calculating formal charge in this molecule, each of the atoms gives us a formal charge equal to or really close to 0, that tells us that this is a stable structure. If not, it tells us it's an unstable structure. So let's start with oxygen. Oxygen normally has a total of 6 valence electrons, right? So I'm just going to go backwards, clean I'm not going to clean all of it. I'll leave this. All right, so we're looking at oxygen first. The number of valence electrons that oxygen normally has is 6. We're going to now look at how many electrons there are in the form of lone pairs and how many electrons there are in terms of bonding pairs. We're going to cut the bonding pair in half, right? We're going to assume that electronegativity here is not playing a huge role. We're just going to cut the total electron count. We're going to divide it down the middle. All right, so total number of electrons in the form of lone pairs, we can see we have 1, 2, 3, 4 electrons in the form of lone pairs, and we have a total of 1, 2, 3, 4 electrons in the form of bonding pairs. We're going to take 1/2 of that count of 4, though, and this is going to give us a total formal charge on oxygen of 6 minus 6, which is equal to 0. The oxygen in this form, as we have it drawn, is actually very stable inside of the molecule. It has the perfect balance of electrons it gets to keep to itself versus electrons that it gets to share. We're not overloading the oxygen, we're not taking too many away. It is perfectly stable in this covalent configuration. We're going to do the same thing for our carbon, and we'll do it for one of our chlorines. Since the second chlorine, again, looks identical to the first, we're only going to have to pay attention to one of them. The formal charge on the other should be equal to the one we find on the first. All right, so carbon normally has 4 valence electrons. We're going to subtract out the number of bonding pairs it has. Turns out it doesn't have any. 0 bonding electrons, plus 1/2 of all of the electrons it has in the form of bonding pairs. Well, there are 2, 4, 6, 8 bonding electrons around it. So we're going to take 1/2 of those, assume that carbon just gets to keep half of the electrons for itself when we're counting formal charge. 4 minus 4 is also equal to 0. Turns out that the bonding configuration that we have for carbon in this Lewis structure is also perfectly stable. It has the just the sweet spot balance between total number of electrons around it in the form of its bonding pairs, and not having any extra lone pairs is actually really good for carbon due to its effective nuclear charge. All right, last but not least, we have chlorine, which normally has 7 valence electrons. And we're going to subtract out the total of lone pair electrons it has, which is 1, 2, 3, 4, 5, 6. We're going to add that to 1/2 of all of the bonding electrons, which we can see is 1, 2. And this is going to give us a total formal charge of 7 minus 7, which is also equal to 0. So in conclusion, if we were to hypothetically pull a lone pair from oxygen to donate it to carbon, what this tells us is that the oxygen is perfectly stable, the carbon is perfectly stable, and the chlorines are perfectly stable because their formal charges are all equal to 0. This is going to be ideal for each of the elements involved. Let's contrast this with our hypothetical structure on the right. Again, our non-equivalent quote-unquote resonance option. If this hypothetically also gives us formal charges all equal to 0, maybe we could make a case that this would actually be a resonance structure, that there would be equal energy. But I am going to kind of preface this, right? I'm leading the witness. We're probably not going to have all 0 formal charges just because the structure is actually different. We may have made atoms dissatisfied if we pulled the wrong lone pair. All right, so let's start with oxygen again. Oxygen normally has 6 valence electrons. We're going to subtract out from this each of the lone pair electrons, 1, 2, 3, 4, 5, 6. And we're going to add to that 1/2 of all of the bonding electrons, 1, 2. Now here we are going to be taking 6, and we're going to be subtracting 7 from that. This tells us that the formal charge on this oxygen is -1. This oxygen is actually a little dissatisfied. It has 1 too many electrons present on it. It has too many lone pairs. It would actually be more stable had it been able to donate that electron density like how our oxygen on the left did. Let's see if this change affected our carbon though in any way. Carbon also has, again, 4 valence electrons, and we're going to subtract out all of the lone pairs it has, which still doesn't have any, plus 1/2 of all of the bonding pairs. So this carbon has 2, 4, 6, 8 electrons in the form of bonding pairs, And it turns out that this change that we've made in terms of where we pulled the lone pair from doesn't actually affect carbon at all. As long as carbon has a total of 4 bonds around it in any configuration, so here we have 2 singles and a double, carbon's perfectly satisfied. So if the oxygen, though, has a -1 charge and our carbon has a 0 charge, this must mean that another element somewhere has to have a positive charge because, according to our rule over here, the sum of all of our formal charges has to equal the sum of the total molecule's charge. So there are only 2 places left. We have our chlorine on the right and our chlorine on the left, which now both of these things are like, they look different. One has a double bond, one has a single bond. Now the single bonded chlorine has the exact same configuration in the molecule as our example over here. For this reason, we can assume that this chlorine has also a formal charge of 0. It is in the exact same configuration, it has the exact same balance of lone pairs to bonding pairs, so we can assume that this is going to be perfectly stable. The only new configuration is our poor chlorine on the left. This chlorine has lost one of its lone pairs. It now is being forced to share that lone pair with carbon. And sometimes, again, like in oxygen's case, this leads to nice stability, but since we've run out of options here, we can already suspect that this chlorine is going to have a +1 formal charge. So let's actually check this out and confirm that suspicion. Our chlorine normally has 7 valence electrons. We're going to subtract out our 1, 2, 3, 4 bonding, our lone pair electrons, add to that 1/2 of the bonding pair, which is 1, 2, 3, 4 electrons. And this gives us a total of 7 minus 6, which is +1, what we expected to see. Our oxygen has a -1 formal charge and our chlorine has a +1 formal charge. These two things do balance out and give us a 0 formal charge overall across the entire molecule, but we want each of the atoms in our molecule to be perfectly stable. What this tells us by observing our formal charges, as we've done here, is that although we could have hypothetically pulled a lone pair from either the oxygen or the chlorine, one of these options actually gives us a stable result, and the other gives us a less stable result. This means that we do not have any type of resonance option with this particular molecule. There is just one stable output, one stable Lewis structure that we can draw that is going to be the more likely case because of its minimized formal charges. All right, so this formal charge argument we can also use as we move forward and really start doubling down on looking at the more exceptional Lewis structures, the ones that are going to start breaking the octet rule. Right, now that we've been observing the octet rule really for like 6 days at least, if not more, we're finally at the place where we can observe when it's okay to break it. The first example, the first case we're going to talk about when it's okay to break our octet rule are these molecules, which fall under the category of being called free radicals. Free radicals are structures that have an odd number of electrons in them. This means that there will always be at least one unpaired electron in the Lewis structure somewhere. These molecules, because there are unpaired electrons, are highly reactive and very short-lived, right? Either they want to get rid of that one unpaired electron or they want to gain just one more electron as quickly as they can. These free radicals are, in part, as like a really good example of like how reactive they are and where they can be found, are actually involved with the process of aging, or decomposition, kind of both in a morbid sense. Anyway, if we observe our banana, the fresh kind of pre-ripened banana, this green banana is present on the left, and what causes this banana to slowly age, gain more spots until we see our banana here on the far right is now perfect for banana bread. What causes this process is the existence of free radicals, both kind of existing in the atmosphere around it, as well as during the aging process, free radicals being produced and then immediately used up to further the aging process. It's sort of like a self-perpetuating process. One way that we can stop this process, or at the very least slow it down, to slow down the damage that these free radicals can do, is by adding an antioxidant. It turns out that a free radical reaction tends to follow the form of what is known as an oxidation reaction. And we'll be talking about what this label really means more in Chapter 9, but we can see just by knowing what its name is, really why antioxidants are called what they are. These are other molecules that are going to stop oxidation. If they are able to stop oxidation, or at least slow the process of oxidation, we can slow the process of free radicals causing all of this damage and decomposition. So antioxidant molecules can also be found pretty freely out in the wild. This is what leads to certain foods as being labeled as superfoods, things like blueberries, spinach, acai berries, etc. These all contain molecules that sort of act as free radical sponges, and again can halt, or at least slow, that oxidation process. Alright, so free radicals though are what we are focusing on here. Bananas aside, we are going to be observing molecules from here on out that may possibly contain a number of unpaired electrons. Alright, so let's get a good example in, get some practice in. When should we recognize free radicals out in the wild? How do we know we're going to be working with something that has an unpaired number of electrons? Well, a really good first example is by drawing the structure of the molecule nitrogen monoxide, or NO. There are two stables at first that kind of become apparent that they may be structures for nitrogen monoxide. However, by using the formal charge method that we just learned, by observing the formal charges in this hypothetical case, we can determine which, if either, of these two structures is going to end up being the most stable. Alright, so try drawing the structure of nitrogen monoxide, use formal charges to determine which structure is going to be the most stable, and then we can compare our answers. Alright, welcome back. Let's use the method that we've already learned, right? Just because we're finding exceptions to the octet rule doesn't mean we are going to entirely throw out our rules for drawing Lewis structures. We are still going to be following those rules, just now we can use formal charge as almost like a hidden rule number 9 to determine when it's okay to not actually have a complete octet. Alright, so our radical nitrogen monoxide is going to have a total number of valence electrons equal to 5 from the nitrogen plus 6 from the oxygen, giving us a total of 11 valence electrons. And here we can already see, before we start drawing the Lewis structure, we have an odd number. This means that there will be an unpaired electron somewhere. Our electrons are more stable when paired, but in this case, we are going to be working with a free radical. Something is going to be 1 electron short. As we start drawing the structure for nitrogen monoxide, we can see the skeletal structure here. We don't really have one atom in the center, rather the two are just bonded to each other. We have currently used 2 electrons from the pool, meaning that there are still 9 electrons left to place. Which of these 2 counts, though, as like the terminal atom? Well, let's pretend that it doesn't matter, because it really doesn't. There is no central atom. Again, they're both in a partnership. NO. So let's say in one case, we're going to start adding our 9 electrons, or we're going to start by adding them on the nitrogen and then move to oxygen. In the other case, we'll start with oxygen and then move to nitrogen. So there are 2, 4, 6, 8, 9 electrons that can be placed, and here we see oxygen now is left with, it's left hanging with an unpaired electron. Or in the right-hand case, 2, 4, 6, 8, 9, and it's nitrogen that's left with an unpaired electron. So there are 2 different options here, and we can build off of either of these options, and that's perfectly valid for now. We're going to observe formal charge once we are finished trying to satisfy the octets as best as we can. Currently, in our structure on the left, our nitrogen has 8 valence electrons, and the oxygen has 2, 4, 5 valence electrons. Well, we're not going to get to a total of 8 on both sides, but we should try to get as close as we can. So we're going to take a lone pair from the nitrogen, move it into the center. This gives us still 2, 4, 6, 8 electrons on the nitrogen, 2, 4, 6, 7 electrons on the oxygen. And this is as close as we can get to 8 without going over. Similarly, with the structure on the right, the nitrogen only has 5 electrons around it, so we're going to take a lone pair from the oxygen and move it in towards the center. This means that now we have 2, 4, 6, 8 electrons on the oxygen and 2, 4, 6, 7 electrons on the nitrogen. Currently, we are as close as we can get to satisfying all of the octets, but we have 2 unique structures. One, with the free radical electron present on the oxygen and the nitrogen being satisfied. I'm just cleaning up the structures here. And the other, where the free radical is on the nitrogen and it's the oxygen that's perfectly satisfied. So let's determine what the formal charges are to really double check which of these 2 options is going to be the best option for the molecule. All right, well, nitrogen normally has 5 valence electrons, and we're just going to follow the same method that we've used before in our previous example. There are 1, 2, 3, 4 lone pair electrons, and we're going to add that to 1/2 of the bonding electrons, which is a total of 2, 4. This gives our nitrogen a total of a -1 charge, right? We're taking 5 and we're subtracting out a total of 6 in here algebraically. This gives us a total of -1. The oxygen with the unpaired electron normally has 6 valence electrons. It currently has 3 electrons in the form of lone pairs, and there are also 4 electrons around it in the terms of a chemical bond. This means that the formal charge on our oxygen in the structure on the left is a +1. So these 2 will cancel each other out across the whole molecule, which matches our nitrogen monoxide not having a charge. However, we can see that between the 2 options here, the oxygen and the nitrogen both have formal charges independently. If the other structure has formal charges equal to 0, we know that it is going to be the more stable option. So let's check it out. Our nitrogen, same thing, same process, 5 valence electrons. We're going to subtract out the 1, 2, 3 lone pair electrons and 1/2 of all of the bonding electrons, which there are 4 here present. This gives our nitrogen now a formal charge of 5 minus 5, which is equal to 0. And our oxygen, with its 6 normal valence electrons, currently surrounded by 4 lone pairs and 1/2 of 4 bonding pairs, also has a formal charge equal to 0. So despite the fact that nitrogen has an unpaired electron right here, this unpaired electron actually gives it a formal charge of 0. So although nitrogen's octet is not satisfied, this is as close as we can get, and our consolation is that this nitrogen in this form actually has the perfect balance between bonding pairs and lone pairs and enables it to be perfectly satisfied, or at least satisfied enough. All right, so between these 2 options, we're going to circle this boy. This one is our most stable structure determined using formal charges. These 2 are not in resonance. Because of the difference in formal charges, we can conclude that they have different energy levels. They are different structures. If these were actually resonant structures, all of the formal charges present would be the exact same. Okay, our second exception to the octet rule is known as the Boron Problem. Boron on the periodic table is more on the right-hand side. It counts as a non-metal. And non-metals, as we have also talked about before, characteristically tend to gain electrons. However, boron only has 3 valence electrons. And as we've talked about before, we're always trying to find that path of least resistance. What is the easiest way to reach the octet? It's easier for boron with its 3 valence electrons to actually lose electrons in order to satisfy its octet. So here we have 2 competing natures inside of boron. And as a result, it doesn't really pick. It's kind of caught in the in-between. Boron has a lot of really interesting chemical properties as the result of this issue, but it also gives us an issue when trying to draw what the best Lewis structure for boron is inside of molecules. So for example, if we look at boron trifluoride, which is illustrated down below, we've already gone through the steps here. This is, at least at cursory glance, what the most stable structure is until we observe what the octets are for each of the elements. Fluorine, in each of these 3 locations, has 2, 4, 6, 8 electrons perfectly satisfied. Boron, however, only has 2, 4, 6 electrons. It is tentatively dissatisfied. But if we take the time to actually observe the formal charges for each of these unique element types in the structure, fluorine, we would calculate, and I'm going to leave this as an exercise to the viewer for additional practice, fluorine has a formal charge of 0 in this case, in this form. Our boron, and this one I will calculate explicitly to show where it's coming from, boron with normally 3 valence electrons, no lone pairs, and we're going to take 1/2 of all of the bonding pairs equal to 6, 3 minus 3 is equal to 0. Even though boron has an incomplete octet, because of its strange nature where it's always kind of competing with itself, it turns out that having 6 valence electrons around boron is stabilizing enough for this molecule to exist in this form, as it is. The Lewis structure that we have drawn here is sort of dissatisfying because we can't complete boron's octet. But it's satisfying enough for boron because our formal charge is equal to 0. So this is a good example of another molecule where an element is going to be breaking the octet rule. Boron, yes, only has 6 valence electrons, but just like the free radical problem we just looked at, sometimes the lack of electrons is actually going to stabilize an element based off of what its formal charge is. All right, so we have one last example to discuss, and it's the strangest example of all. We are going to now be looking at what happens, or rather how we can expand the octet of an element. So we first introduced why we need 8 electrons by using this glass of milk, right? And we described the octet rule by stating that in your valence shell of an element, of an atom, you have 1 s orbital and you have 3 different p orbitals. If you place 2 electrons in each of these orbitals, we are going to slowly fill up the glass. Once the glass is filled, we have a total of 8 electrons in your valence shell. Right, your valence orbitals can only hold 2 electrons per orbital, giving you 8 total. And it makes sense if we need to draw structures that have unfilled octets. This means that we just don't place this last pair of electrons, or maybe we have 1 free radical electron, but the milk is still going to fit inside of this glass. Structures with filled octets fill this glass perfectly. So in our last category of octet rule exceptions, when we expand the octet, how do we do this? We do this by allowing for the existence of d orbitals. Now, we haven't talked about the influence of d orbitals in and around the valence shell yet, but if your element is close enough in energy, if its valence shell is close enough in energy to nearby empty d orbitals, we can kind of use these as back pockets to kind of store extra electron density. So in this class, like in general chemistry, we're not going to be going into the details of how this happens. We're going to leave that for an upper divisional class. So again, if you find this interesting, please continue in your chemical education. But for here, we're going to be using this as sort of like an asterisk, a hand-wavy explanation to say we can expand the octet, provided we pay attention to what atom is actually bonding in the structure, and we acknowledge whether or not it will even need to expand the octet. Sometimes this happens, sometimes this doesn't. So let's talk about some additional addendums to our Lewis structure rules to really figure out when are we allowed to expand the octet? When is it necessary? Lewis structures, or rather, elements in Lewis structures, can have more than 8 electrons. They can expand their octet only if the 2 following points are true. First, the expanded octet must result in some type of minimized formal charge. In other words, if the molecular structure prior to expanding the octet does not have all 0 formal charges, or if it's not as minimized as it can be, sometimes pushing the electrons around and expanding your octet is going to result in lower or more minimized formal charges. If that's true, the molecule has incentive to expand an element's octet. Second point, your central element, aka the one expanding its octet, must be element number 13 or greater on the periodic table, and it must be surrounded by very electronegative elements. Things like oxygen, or chlorine, or nitrogen, or fluorine. This is not an exhaustive list, etc. They need to be in the upper right-hand corner of the periodic table. So a really good example of a molecule that we can draw and then kind of critically evaluate is that for the chlorate ion. Chlorate has the chemical formula of ClO3-. And if we follow all of the previous rules, all of our Lewis structure rules, follow the rules, we would end up with the structure that we can see here slightly to the right. Each of the atoms in this structure has a satisfied octet, and there is a total of a -1 charge being present in the structure due to the -1 charge in the chemical formula. So everything seems, at least at cursory glance, like it's totally fine. As an additional double check, not just counting the octets is everything satisfied, but as an additional point, we should get in the habit of always double checking the formal charges of each of the elements inside of the structure. This is going to tell us whether or not our structure is actually as stabilized as it can be. So let's determine what the formal charge is on each of the elements inside of this structure, or at least each of the unique elements, right? We can see that there is an oxygen, or 3 different oxygens present, but each of them has the same bonding form. Each of them looks like it's attached to chlorine in the same way, and then we have chlorine in the middle. So our oxygen, and I'll write here, I think I'll have more space here. So our oxygen normally has 6 valence electrons. There are currently 1, 2, 3, 4, 5, 6 bonding electrons, or lone pair electrons, sorry. And we're going to add to that the bonding electrons, 1/2 of that total, and that total is equal to 2. The total formal charge on this oxygen is going to be 6 minus 7, which is equal to -1. Since each of the oxygens present in the structure looks the exact same, they're also each going to have a formal charge of -1. So far, we can already see that we do not have minimized formal charges. There's plenty of negativity to go around. And the counter positivity has to be in the center here. So let's observe chlorine's formal charge real quick. Chlorine normally has a valence count of 7. We're going to subtract out the total number of lone pairs it has, so that's equal to 2. And we're going to add to that 1/2 of the total number of bonding electrons, which is 2, 4, 6. The total formal charge on this chlorine is a +2. So not only is it a +1, it's a +2. This is actually relatively far from 0 in terms of like the total charge count. Chlorine is also a very electronegative atom, so the fact that it has a positive charge is already a bad sign. What this tells us is that even though this structure that we have drawn so far for the chlorate ion, even though each of the elements has a complete octet, none of the octets are actually structured in a way that makes the atom really stable. So what we're going to start doing is pushing electrons around. Since each of these oxygens has 2 negative of a charge, right? They're each -1. They're 2 negative. Oh, I need to get a blue pen. There. Each of them is 2 negative. We're going to push an electron pair away from the oxygen to the chlorine. And we're just going to do one, at least at first. We're going to push one of these lone pairs away from the oxygen to remove some of its negativity, and in pushing it to the chlorine, we're also hopefully going to be removing some of chlorine's positivity, right? We're giving it some extra electron density. So now we have an oxygen up on top with a double bond to this chlorine. We have, in the process, expanded its octet. Currently, there are 10 electrons around this chlorine. However, we can expand its octet because we are trying to minimize the formal charge. In addition, chlorine is greater than element number 13 on the periodic table, and it's bound to a bunch of oxygens, which are very electronegative. So each of these 3 points that must be true, are true, and we're trying to fix this structure. We're trying to make it better. We're trying to make it more stable. All right, so the formal charge now on our oxygen, we can calculate 6 minus total lone pair electrons is 4, plus 1/2 also of 4, gives us a total of 0. This oxygen, as we have taken a lone pair and pushed it to chlorine, has actually improved its stability. Each of these oxygens, sadly, we haven't touched yet, so each of them still has a -1 formal charge, and our chlorine in the center, with its normally 7 valence electrons, we're going to subtract out 2 from the lone pair, 1/2 from the 2, 4, 6, 8 electrons around it, and this is going to give it a +1 charge. Right, we're taking 7 minus 6 gives us +1. Well, if taking 1 pair of electrons from an oxygen and pushed it to chlorine dropped its formal charge from a +2 to a +1, if we took another lone pair and pushed it towards chlorine, we could remove this. And in doing so, we would also alleviate the stress that is on one of our other oxygens. So let's do that, right? We've already expanded chlorine's octet once. Let's do it again. In doing so, we are going to be minimizing the formal charge count as much as we possibly can. We're going to take this lone pair, push it towards our chlorine. In doing so, we have now created another oxygen that looks like our first, with a formal charge equal to 0. And our chlorine now has, we can reestablish what its formal charge is, now is going to have a formal charge of 7 minus 2 plus 1/2 of 2, 4, 6, 8, 10. And when we crunch the numbers, we're taking 7 minus 2 plus 5, which is equal to 0. And in illustrating our structure this way, in expanding chlorine's octet, we have now minimized 3 different elements' formal charges. This last oxygen present is going to have to remain with a -1 charge. To revisit one of our previous rules, the total of all of the formal charges across all of the elements must equal the charge of the molecule itself. So because the chlorate ion has a -1 charge, one of our atoms inside of this molecule must have some type of negative charge. Now, oxygen is a fairly electronegative element. It is going to be able to stabilize this negative charge pretty easily. And in fact, now that we have created a structure like so, where in the process we could pick and choose which oxygens we pulled lone pairs from, we could actually go even further and draw a bunch of resonance structures that are equal in energy, equal in form, across the board, and would actually be able to disperse and stabilize this negative charge even more. We are not going to spend the time drawing those resonance structures, but I would invite you to try that out for yourself. There should be 3 different resonance structures when in combination are going to give us the most accurate picture that we can possibly draw for how this molecule would look and behave characteristically. All right, so this is how we can expand our octets. This is how we know we can even expand our octets. Like, what's the motivation? We want to minimize our formal charge. That is the primary motivator. If we can minimize formal charge even more, than our base Lewis structure, this is going to be the reason why we're going to try and expand an octet. We can further do so, however, if your atom, again, is greater than number 13, and if it is bound to very electronegative elements. If your central atom is not greater than number 13, you cannot expand the octet. If your atom and its atomic number Z is less than, or just less than, not equal to, less than 13, this means that it has no available d orbitals to hypothetically push this excess electron density into. Because there are no available d orbitals, elements that are less than number 13 on the periodic table cannot expand. Similarly, if your atom is not bound to very electronegative elements, it cannot stably expand its octet. So we have to, again, triple check these 2 points. We can only expand our octet, we can only break the octet rule if these following statements are true. All right, so I'm going to ask you guys to test out your metal. Draw at least one resonance structure, because there are a number of different options. Draw one resonance structure for the sulfate polyatomic ion, and do so, find that one resonance structure at least that's going to have a minimized formal charge. All right, so we are going to come back together, draw this one last structure for the day, our one last Lewis structure for chapter 6, and then we're going to wrap it up with a nice bow. That's not to say that obviously we're not going to continue drawing structures, but we have learned all of the rules necessary to draw both the base level and the exceptional level of Lewis structures. All right, so we're going to follow our rules for drawing sulfate before we can establish whether or not we can break them. Right, we can't just jump into drawing an expanded octet. We're going to get a base level foundational structure by following the rules first. So our sulfate is going to have a total of 6 valence electrons from the sulfur, plus 4 times 6 electrons from each of these oxygens, plus an additional 2 from the -2 charge. So we're going to have 2 extra electrons in the structure, giving us the -2 charge. The total number of valence electrons, therefore, is going to be equal to 32 valence electrons. So we're going to take each of these 32 electrons away from the atom, or the atoms in the molecule, and then we will start redistributing them as we need to. Now, between the sulfur and the 4 oxygens, each of these atoms has the exact same bonding capacity. So how do we know which one's going to go into the center? Well, between each of these atoms, sulfur is kind of the odd man out. So even just conceptually, if we're paying attention to things like symmetry and aesthetics, it would make sense for the sulfur to be in the middle and our 4 oxygens to be around it. Another way to kind of critically evaluate and determine that the sulfur is going to be in the middle is that sulfur has an element or an elemental number that is greater than or equal to number 13, which means that it has the potential to expand its octet. This rule of thumb doesn't always mean that you will have to expand your octet, but it's kind of something nice to look out for. If you have an element that is greater than number 13 in some type of structure, it may end up being in the center in order to accommodate an expanded octet. All right, so for all of these reasons, we place sulfur in the middle, oxygens outside. We have currently placed 2, 4, 6, 8 electrons in the structure, giving us a total of 24 electrons left. So we're going to take those 24, place them around the terminal atoms first. We're still going to follow that rule. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, and 24. So all 24 of the electrons have now been placed around our oxygens in the terminal positions. No electrons left in the pool. Because we have no electrons left in the pool, this is going to be the point where we can kind of look at and establish are all of the valence counts, or all of the octets satisfied. And after that, as now kind of a new additional critical evaluation, we're going to calculate formal charges. All right, so our oxygens each have 2, 4, 6, 8 electrons around them. Sulfur also has 2, 4, 6, 8 electrons around it. This means that all of the octets are satisfied. Oh, and of course, because we have a -2 charge here, we're going to add a -2 charge in brackets around it. Before we call this good, though, we're going to have to, again, establish what are the formal charges. If this structure has minimized formal charge, then, like, perfect, we're done. We can just wash our hands of the problem. We have the most stable Lewis structure. If it is not the most stable Lewis structure, though, we're going to have to start pushing electrons around and expanding an octet, right? We're going to have to break the octet rule to make something even more stable. So let's start with our oxygens. Each of these oxygens looks the exact same. They all have the same kind of characteristic bonding pattern. Let's see, so I'll do this one. Each of these oxygens has 6 valence electrons. We're going to subtract out our 1, 2, 3, 4, 5, 6 total lone pair electrons. We're going to add that to 1/2 of the bonding pair, which is 2 electrons present. This gives us a -1 formal charge, and that's going to be true for each of these oxygens around the structure. Now we can already kind of see that we are going to end up in a situation just like the chlorate ion before, where the valence shells are all completely filled. We have nice complete octets, but it looks like all of the formal charges are kind of pushed away from the minimum. We don't have the ideal electron distribution across the entire molecule. All right, our sulfur, just to be explicitly clear, is going to have a formal charge of 6 minus no lone pairs plus 1/2 of 8, 2, 4, 6, 8 in all of the bonding pairs, giving us a total of +2. Yeah, this sulfur definitely does not have a minimized formal charge, so we're going to have to start pushing some electrons around. In fact, the total formal charge of the sulfur in the center tells us how many lone pairs from surrounding oxygens we should push. In order to give sulfur the amount of electron density it needs to reach a formal charge of 0, we're going to need a total of 2 more pairs of electrons to come in towards it in the form of bonding pairs. So here's where the aspect of resonance comes in. We have 2 electron pairs necessary to push towards sulfur, and we have 4 different options from where we can grab these electrons. So I'm just going to pick this pair up on top, push this one in towards the center, and I'll pick this one. Because why not? Again, we could have picked from the oxygens on the left or right. We could have picked like top and to the right, like any of these combinations would do, just so long as we have 2 additional bonds, 2 double bonds present in towards this sulfur. Because we've pushed 2 additional bonds in towards the sulfur, there's now a total of 2, 4, 6, 8, 10, 12 electrons bonded to it, right? 12 electron pairs in the form of bonding. This means that now as we adjust the count for our formal charge, 6 valence electrons, still no lone pairs, but 12 total bonding pairs gives us a total formal charge equal to 0. And the oxygens that we've taken the electrons and pushed them in towards the center, we get a different electron or a different formal charge count for them, since there are 6 valence electrons minus 4 lone pairs plus 1/2 of 4 gives us a grand total of 0. So now we have a sulfur that is completely satisfied. We have 2 oxygens, this one as well, that are completely satisfied. And we have 2 oxygens also left over with that -1 formal charge. Sadly, these are going to have to be left as is. Again, since we're working with a polyatomic ion, the total count, the sum of all of the formal charges inside of the molecule, must equal the charge of the molecule on the whole. So we have a -1 formal charge on one of our oxygens, a -1 formal charge on the other oxygen, the sum of this is -2, and there is a total of a -2 charge present in the sulfate anion. So this structure that we have drawn, in fact, I'll just write a cleaner version over here, is the most stable Lewis structure that we can draw for sulfate, at least in one of its resonance forms, and we can conclude this because we have minimized the formal charge. We had to expand sulfur's octet to do it, but again, because it's greater than element number 13 on the periodic table, it has access to those high energy empty d orbitals where it can just slip all of the electron density into that back pocket. We don't have to worry about the expanded octet. The electrons have places to go. We're not explicitly paying attention to what that new electron configuration is in general chemistry, but suffice to say that the electrons are stable where they're going. They have a place. And that is the end of chapter 6. So here we have a couple of additional example problems, again, pertaining to keeping track of the formal charge in your molecules, as well as when you know you can break the octet rule, whether or not you're going to be working with something like a free radical, something like boron, or something with an expanded octet. There are a lot of checks and balances that we have in order to determine whether or not we need to break the octet rule, or if we're actually more stable not breaking the octet rule. But that type of critical assessment is going to be something that we're going to have to really learn with practice, so I would strongly suggest working through the section review problems here. Alright, if you have homework, please double check and do your homework, but until next time, class is dismissed.